Fundamental properties of complement sets. Welcome, everyone. Before we dive into today's new material, let's take a quick moment to reflect on what we have already covered. In our previous lessons, we established the fundamental definition of what a complement of a set actually is, and we practiced how to visualize those complements using Venn diagrams to see the regions clearly. Now, moving forward into this new subsection, we are going to shift our focus from just visualizing sets to exploring the algebraic properties of complement sets. This means we will be looking at the mathematical rules and laws that govern how these sets interact with one another. You might wonder why this matters. Well, mastering these properties is absolutely essential because they provide us with the tools needed to simplify much more complex set expressions, much like how you use algebraic rules to simplify equations in algebra. Furthermore, understanding these laws is not just about set theory in isolation. These properties are fundamental building blocks for the study of Boolean algebra and are vital for anyone pursuing more advanced mathematics. So, let's get started by looking at our first set of laws. The complement laws. First, let's look at Part A, which is the union law. This is written as, a union A prime equals U. In plain English, this law tells us that if you take a set and combine it with everything that is not in that set, you end up with the entire universal set. Think about it this way. If you gather everything inside set A and everything outside of set A, you have accounted for every single element in our entire universe. To make this concrete, let's use a real-world example. Imagine our universal set, U, represents every student in a grade XI classroom. Now, let's define set A as the group of students who have finished their mathematics assignment. Naturally, the complement, which we call a prime, would be the group of students who have not finished that assignment. If we follow a simple three-step process, first, identifying the students who finished the work, second, identifying those who didn't, and third, combining both groups together, what do we get? We get the entire class. There is no third option. Every student either finished it or they didn't. Therefore, a union A prime equals the universal set. Now let's shift our focus to Part B, the intersection law. This is written as, a intersection A prime equals the empty set. This law is actually the logical flip side of the first one. It states that there is no overlap between a set and its complement. It is logically impossible for an element to be inside set A and, at the exact same time, be outside of set A. Let's return to our classroom scenario to prove this. Suppose we are looking for a student who is in set A, meaning they completed the assignment, but we also want them to be in set A prime, meaning they did not complete the assignment. If we try to find a student who satisfies both conditions simultaneously, we will find no one. It is a contradiction. Because no student can both complete and not complete the same task, the intersection of these two groups is an empty set, or an intersection A prime equals the empty set. Now that we have a clear understanding of what a complement is and how to visualize it using Venn diagrams, let's move into the core of today's lesson, the algebraic properties. On this slide, we are going to look at the two most fundamental laws, the union law and the intersection law. Keep these two laws in mind because they are the building blocks for the more advanced properties like double complementation, which we will cover in the next slide. The law of double complementation. Now that we have mastered how a set and its complement interact through union and intersection, let's move on to a very intuitive concept, the law of double complementation. Symbolically, we express this law as a prime inside another set of parentheses, prime, equals A in simpler terms. The complement of a complement brings you right back to where you started. To make this crystal clear, let's look at a real-world example involving a simple light switch, which can only be in one of two states, on or off. First, let's define our boundaries. Let our universal set, U, consist of the two possible states, on and off. Now, let's define set A as simply the state on. To understand the double complement, we follow a two-step process. Step 1, we find the first complement, which we call a prime. Since the complement represents everything in the universe that is not in our set, the complement of on must be off. So, a prime equals the set containing only off. Step 2, now we take the complement of that result. We are looking for the complement of a prime, which is written as a prime, inside parentheses, prime. If we ask, what is the opposite of off? The answer is on. As you can see from our conclusion, by applying the complement twice, we have returned to our original state. Therefore, a prime equals A. It is much like how a double negative in English cancels out to create a positive statement. Laws of empty set and universal set. Now that we have mastered how a set interacts with its own complement and how the double complement returns us to our original set, let's look at what happens at the two extreme ends of the spectrum. On this slide, we are exploring the laws of the empty set and the universal set. Think of these as the boundaries of set theory. First, let's look at part A, the complement of the empty set. We represent the empty set with the symbol phi and its complement as phi prime. The law states that phi prime equals U, which is our universal set. Now, why is this true? Well, remember that the empty set, by definition, contains absolutely no elements. If we ask the question, which elements are not in the empty set? The answer is everything. Since every single element in our universe is technically not in the empty set, the complement of nothing must be everything. So, the logic follows that the complement of the empty set is the universal set. Moving on to part B, we have the complement of the universal set. Here, we take the universal set, U, and find its complement, U prime. The law tells us that U prime equals the empty set, or phi. This is the exact opposite of what we just discussed. The universal set is all-encompassing. It contains every possible element under consideration. Therefore, if we try to find elements that are not in the universal set, we won't find any. There is simply nothing left outside the universal set. Because there is no space left outside the boundaries of U, the result is an empty set. So, to summarize these two extremes, the complement of nothing is everything, and the complement of everything is nothing. In our next slide, we will look at some common pitfalls where students often get these boundaries mixed up. Common mistakes to avoid. First, many students find themselves confusing the union and the intersection laws. You might accidentally swap the results, writing that a union a prime equals the empty set, or that an intersection a prime equals the universal set. To keep this straight, remember the logic we used in our classroom example. The union symbol, which looks like a U, is for combining or uniting everything. When you combine a group with everyone outside that group, you naturally cover the entire universe. On the other hand, the intersection symbol looks like an N and is looking for common ground. Since a set and its complement are, by definition, opposites, they have nothing in common, which is why the result must be the empty set. Second, be careful not to ignore the universal set. A frequent error is trying to calculate a complement without first identifying what your universe actually is. Always remember that the complement, a prime, is entirely dependent on the boundaries of the universal set. If you don't know what is in your universe, you cannot accurately determine what is outside of set A. Finally, watch out for misinterpreting the double complementation law. It is tempting to think that applying a complement twice, written as a prime, all in parentheses, results in just a prime again. However, as we saw with our light switch example, the two knots essentially cancel each other out. Just like a double negative in English, the second complement brings you right back to your original set, A. Now that we have covered the fundamental laws, I want to pause and discuss some common pitfalls. As you move into more complex set theory problems, it is very easy to make certain errors, so let's look at 3 specific mistakes to avoid. Keep these distinctions in mind as we move to our final slide, where I will provide a summary table of everything we have learned today. Key takeaways. All right, we have reached the end of our lesson. To wrap everything up, let's take a final look at this summary table. This is your cheat sheet for the fundamental properties of complement sets that we've covered today. I highly recommend reviewing this table whenever you are solving complex set algebra problems. First, let's revisit the complement law for union. As we saw in our classroom example earlier, a union a prime equals U in simple terms. A set plus its opposite equals everything in the universal set. Next, we have the complement law for intersection. This is the logical opposite. A intersection A prime equals the empty set. This reminds us that a set and its opposite have absolutely nothing in common. Third, we have the law of double complementation. Symbolically, this is a prime equals A, just like the light switch example we discussed. The opposite of an opposite brings you right back to the original set. Moving on to the extreme cases, let's look at the complement of the empty set. We know that empty set prime equals the universal set. Essentially, the opposite of nothing is everything. Finally, we have the complement of the universal set. This is U prime equals the empty set. This simply means the opposite of everything is nothing. If you can master these 5 properties, you will have a very strong foundation for the more advanced topics we will tackle in our next session. Great job today!